In this video, we're going to look at a context where we can chain together two function processes in a useful way. So suppose a rock is thrown into a lake, creating a circular ripple that gets larger over time. The radius of the ripple increases by 8 centimeters per second. Let's draw a little diagram of this just to make sense of it. So we drop a rock into the water, and then the rock makes a circular ripple in the water, and the radius of that circular ripple increases at 8 centimeters per second. So at some point later in time, the circular ripple has a larger radius. So that circular ripple is growing as time passes. Let's define a couple functions to help us out here. So if we know the radius of the circular ripple is r centimeters, then we define a function f that gives us the area of the circular ripple in square centimeters. So f of r would be equal to pi r squared, because that gives us the area of the circular ripple in terms of the radius of the circular ripple r. Now we could also define a function g that takes as its input a number of seconds t since the rock hit the water, and then outputs the radius of the circular ripple. And since the radius of the circular ripple increases at 8 centimeters per second, 8 times t gives us the radius of the circular ripple t seconds after the rock hits the water. So let's suppose we want to know the area of the circular ripple 3 seconds after the rock hit the water. So I'll erase out some of this diagram. We'll imagine the rock hitting the water, and then 3 seconds pass, and then we have the circular ripple like that. We'll just write 3 seconds to keep that in mind. Now the circular ripple has some radius. The function g will give us the radius of that circular ripple in centimeters given a number of seconds t. So g of 3 will give us that radius of the circular ripple. And g of 3 is equal to 8 times 3, which equals 24. And therefore, the radius of that circular ripple is 24 centimeters, 3 seconds after the rock hits the water. Now, the function f will take a radius of the circular ripple as its input and then output the area of the circular ripple. So if the radius of that circular ripple is 24 centimeters, then f of 24 will represent the area of the circular ripple. And f of 24 is equal to pi times 24 squared, and that's equal to about 1809.56. So we can say that 3 seconds after the rock hits the water, the radius of the circular ripple is 24 centimeters, and therefore the area of the circular ripple is 1809.56 square centimeters. Now let's do this in generality. Let's suppose t seconds have elapsed, where t is some varying number of seconds. And so we'll draw a diagram. We'll draw kind of like a frozen state of this. So we'll imagine freezing the situation at some point in time. We'll just say that t seconds have elapsed since the rock hit the water. We know that the radius of the circular ripple, t seconds after it hits the water, is 8 times t. So 8t gives us the radius of that circular ripple in centimeters. Then we know that the area of the circular ripple is pi times r squared. That'll give us the area if we know the radius. In this case, the radius of the circular ripple is 8t centimeters. So this whole expression right here gives us the area of the circular ripple. We could also simplify this a little bit. We could rewrite this a little bit if we wanted. So pi times 8t squared is really equal to pi times 8t times 8t. So the superscript 2, that exponent of 2, means we're going to have two factors of 8t in there. When we look at pi times 8t times 8t, we can multiply the 8's together and the t's together, and then rewrite this as pi times 64, which is 8 times 8, and then times t squared. And we could also maybe write that as 64 pi t squared. So same value, it represents the same quantity, just written in a slightly different way. Therefore, we can say that t seconds after the rock hits the water, the area of the circular ripple is 64 times pi times t squared square centimeters.